Hello there guys, welcome back to another epic Next Real Maths video. We've got another solving differential equations video with Laplace transforms coming right at you. This one will be slightly harder. You'll see why, not crazy harder, but it'll be slightly harder. So let's just dive straight into it guys, not to waste too much time. So as always, let's just write it in better notation. Let's write this as the second derivative of t minus 2 times the first derivative of t plus 5 times just f of t. I was saying derivative of t, derivative of f of t, my apologies, equals 0. Okay, cool. That is our kind of differential equation in f of t notation, which is typical for Laplace transforms. Okay, let's now take the Laplace transform on both sides. I will immediately just apply the linearity straight away, just to not waste space. So I'm going to write this straight up as the Laplace transform of the second derivative for you guys here, minus 2 times the Laplace transform of the first, sorry guys, that should have a derivative sign there, of the first derivative plus 5 times the Laplace transform of just f of t. And that's equal to the Laplace transform of 0 still, because it's a homogeneous equation, so it's 0. Hopefully that makes sense for you guys. That is, again, all I've done is I've applied the Laplace transform to the entirety of the left-hand side and the right-hand side, and then I've just linearized it, I don't know. I've factored everything kind of in a way. I've split it into 3. It's easy to work with that way. Okay guys, now let's actually write out what all of these Laplace transforms are equal to. So the second derivative's Laplace transform is s squared times capital F of s minus s times lowercase f of 0 minus the derivative at 0. That's the second derivative. The first derivative, so we've got minus 2 lots of, is just s times f of s minus lowercase f of 0. And then we've got 5 times just f of s. And that is equal to 0 because the Laplace transform of 0 is 0. Hopefully that makes sense guys, hopefully that's all good. Now actually in the last line on this board, just for space, I will just kind of try and kind of simplify this slightly. So we've got s squared capital F of s. We've said that the boundary conditions are basically f of 0 is 1 and the derivative of 0 or at 0 is also 1. So they're both the number 1 in this case. So we've got minus just s minus another, no just minus 1, sorry. Minus, and then we've got 2 times s times f of s. And then minus, so that's plus 2, plus 5 times f of s equals 0. Okay, cool. Right, let's see what we can do here then in terms of expanding and simplifying and grouping everything up. Let's write this as s squared times capital F of s. What have we got? We've got minus 2s f of s, so let's do that next. So minus 2s f of s. What else have we got, guys? We've got, well, we've got 5 times f of s there, so we can do 5 times f of s. What else have we got? We've got a minus 1, we've got a plus 2, and there's just a minus s, and I think that's it. So there's a minus s, but let's put all of those on the other side. So this is equal to, add the s, so s, and then minus 1 plus 2 is 1, but then it's moving on to the other side, so it's minus. So it's just equal to s minus 1 on that side. Cool. Let's factor the s or f of s out, because at this point, guys, what we're looking for is to get f of s on its own. So this is equal to f of s times s squared minus 2s plus 5 equals s minus 1, like that. Okay, then let's divide both sides to get f of s on its own. So this is equal to s minus 1, all divided by s squared minus 2s plus 5. Again, guys, the s's are s's, and they're not 5s. I mean, there is a 5 there. This is s squared minus 2s plus 5, and that's an s on the top as well. So my apologies, there are a few 5s in this question. I do have to apologise to you guys. Okay, we've got f of s on its own. All we have to do now, guys, we're basically at the end of the question, you could think about it like that. All we've got to do is inverse Laplace transform both sides. So if we inverse Laplace transform both sides, then we get that lowercase f of t is just, we need to work out what the inverse Laplace transform of the right hand side actually is, but I'll just write it as s minus 1 all over s squared minus 2s plus 5. Amazing. Okay, now guys, you might look at that and go, oh, how do I do that? How do I do that? What is that? That's, yeah, it's a tricky one, isn't it? It's pretty tricky. Now you might notice, because in the last video, what we did is we did partial fractions. You might notice that unfortunately we can't do partial fractions on this because s squared minus 2s plus 5 does not have any real roots, which means that it cannot be factorized without complex numbers, and we're not going to do that. So what else could we do? Well, here's the alternative. You can complete the square on the bottom, and I can write this as the inverse Laplace transform of s minus 1 still, but I'm going to complete the square here on the bottom. So if I complete the square, I will get s minus 1 all squared. I've got an extra, that gives me s squared minus 2s, but it also gives me an extra 1 that I don't want. So I'm going to take 1 off, but then there's a 5, so it's going to end up being plus 4. I hope that that makes sense, guys. That's just completing the square. If you expand out everything on the bottom, it will be equal to s squared minus 2s plus 5. Now, guys, you might still be looking at that and going, oh no, what's going on? I'm going to do something to help you. I'm going to write 4 as 2 squared. Okay, what have we got here? Guys, tell me if I'm mistaken, but this kind of looks a little bit like s over s squared plus 2 squared. Tell me if I'm wrong. Well, you can't really talk to me, but it kind of looks like that, right? What's the difference though between s minus 1 over s minus 1 squared plus 2 squared and s over s squared plus 2 squared? This, all the s's are s minus 1s. Does that remind you of something? Maybe I can shift your memory in some way. The first shifting theorem, guys, come on, the first shifting theorem. Okay, so all this is it's just going to, and by the way, guys, what is s over s squared plus 2 squared? Well, like, what is that? That's the Laplace transform of cos 2t. So I'll write that down. Laplace transform of cos 2t is that, okay? So, guys, the Laplace transform, and this is a kind of, I know it's a bit difficult to think backwards like this, the Laplace transform, yeah, of e to the t times cos 2t, using the first shifting theorem, that's equal to capital F of s minus 1, which is this. So this would be equal to s minus 1 over s minus 1 squared plus 2 squared. It's just a shifting, that's all it is, and there needs to be another bracket closing that off, but it is just a shifting. So this is equal to simply, and there should be an inverse here, by the way, guys, I'm very sorry about that. This is equal simply to the Laplace transform, or it's the inverse, so it's equal to e to the t times cosine 2t. And guys, that is really all there is to it. So f of t is e to the t cosine 2t. That's the answer. And guys, that kind of makes sense, that's the answer, right? We've got some initial conditions. The general solution to an equation like this is kind of this form anyway, but there's an extra sign term in there too. But that is the solution to that differential equation, guys. So that is the solution, the particular solution at that, to this differential equation. So just to be really clear on what we did towards the end, because I don't want to lose anyone here, I just want to recap very quickly what we did here in the orange. So this is the first shifting theorem. So it states that, and I will actually write this down because I want it to be very clear, the Laplace transform of e to the at times f of t is the Laplace transform, or it's rather f of s minus a. So it's the Laplace transform of f of t, but shifted to the right by a units. So what we noticed is that this resembles the Laplace transform of cos 2t, but it's shifted to the right by 1 unit, which means we need to multiply it by e to the 1t. That's what we did, and we noticed that the Laplace transform of e to the t cos 2t is this. So just to be really clear, that is what we did there. And that is how we got that answer of e to the t cos 2t. And that's basically, guys, how it goes. In the next videos on Laplace transforms, we'll solve more differential equations, but they'll be non-homogeneous, which means there's going to be a function here instead of 0, which could make it a little bit more exciting. Thank you guys, as always, so much for watching. I highly appreciate it, and I'll see you in the next video. Cheers.